So last time I didn't finish Fibonacci heap, right? So let's try to finish it today soon. So just to recall, what I showed you last time is how Fibonacci heap works, and one of the important thing is that although Fibonacci heap doesn't have as strict structure as binomial heaps, when you do decrease key, is very different, and the structure is not the same. But still, the tree with rank I in Fibonacci heap still grow exponentially, which means that if this is the case, then the maximum rank tree, the tree with maximum rank, is still locked in. Yeah. That's the important thing. And if you look at the cost of each operation, right, in Fibonacci heap, when you insert, you just spend constant time, and then after you add one node, with rank 0 into the collection, you just keep linking until each tree, each rank have only one tree. But yeah, because how many times you can link, right? It's just the number of trees. But the number of trees is just locked in, so the worst case cost is locked in. How about when you delete min? First, you scan through the roots. That takes number of trees. This is locked in. Once you get to the min guy, you delete that guy and get this many children. The number of children become a new trees. So that's you do this many insertions. And after you add this number of new tree into your collection, you keep linking. But overall, each of these is still locked in. Okay? So that's locked in. And for decrease key, you just kind of cut it from, you go to that node that you want to decrease key, just cut it. That takes constant time. And then you keep linking, right? But also you might need to cut many times because there can be propagation, if you remember. Okay. So the number of link is still number of trees, which is locked in. The number of cut is just the height of the tree, which is locked in again. So that's why everything is locked in. But yeah, everything is locked in. But we want to show that we can go beyond worst case. We can get faster amortized time. Okay, so let's see the analysis. And the way to go, one of the very most powerful way to use to do amortized analysis is to use potential function. And the potential function that we're gonna use is 2 times the number of marked nodes, okay, plus the number of trees. So what is, just to recall, when you say that, when we try to bound the amortized cost, right, we look at this thing, which is the real cost plus the potential increase. And if we can bound this thing to be small, then the total cost is going to be small. Okay? The total real cost is going to be small if an AI is small. That's from the previous class. Okay, so let's try to bound AI. Okay? So let's look at the cost of insertion. One sec. How come? Okay, good. Insertion, just again, the real cost is 1 plus the number of link. But now, let's see how potential change. Right? First, you will add one node into the collection, so the number of trees increase by 1. So that is increased by 1. But every time that you link, you decrease the number of trees. So the potential will decrease proportion to the number of links. Right? And now means what? If you look at the amortized cost for insertion, which is the real cost, plus the potential change, then this thing cancel. So you get 2. The amortized cost is just 2. Question about this? Okay, good. Let's see more like other operation. Well, the real cost of delete min is this thing. Okay. And now let's see how potential change, right? Well, the potential will change by this much. And the reason is that first, the number of trees will increase by the number of children minus 1, right? Because you delete one guy, you delete like the min node, that's decrease the number of trees, but you add this many new trees. So that's like the number of children minus 1 new trees. Okay. And again, for each link, you decrease the potential, right? So that's why this is like, you get this decrease in potential. Okay. Yeah, just to make sure that you understand like how to calculate this is just from this definition here, right? Like when I increase the number of trees or decrease the number of trees, that's change this thing. So I just look at how this thing changed. And yeah, now you just sum up the real cost of the amortized cost of delete min plus the real cost of delete min. You sum this thing up, and what you get, well, something cancel again, the link, and you get the number of trees plus 2 times the number of children. Okay, this is still locked in. Doesn't like get something better. Okay, but let's do again. How about decrease key, right? The decrease key for the real cost is 1 plus number of links plus the number of cuts. Okay, there can be many cuts and links, but let's try to analyze how the potential change again. So suppose that, so note again that there can be many cuts. If this is, suppose that if this is the last cut, right? That is, I just delete it and I just mark my parent and I'm done. If this is the case, then what happened? I will decrease the number of trees by 1 because I cut and I put it into my collection. Number of trees increased by 1. But also, now the number of marked nodes increased by 1. So what's the potential change? Can someone tell me? Yeah. 3, yeah, it increased by 3. Because this is plus 2, this is plus 1. Get plus 3. Now, this is now the important thing why they design everything like this. So for every other cut, which is not the last cut, like imagine that you cut this thing, right? And then the guy that is marked before will be double marked, and it will be unmarked, and keep cutting. So what will happen here is that, okay, if you cut, it will increase the number of trees by 1 again, but it will actually decrease the number of marked nodes by 1, right? Because your parent, which used to be marked, will be unmarked now. Okay, which means what? The change in potential is now minus 1. Because this is minus 2, this is plus 1. Okay. This is actually exactly why we use like we choose the coefficient there to be 2. This is so that like this thing is stronger than this thing, so you get some you get decrease in potential, which is good for you. Okay. So now we are ready to analyze the amortized time for decrease key. So the change in potential, the last cut will increase the phi by 3. Every other cut decrease phi by 1. So this is the total decrease by the cut. Like all the cut might except the last guy would decrease the potential. And how about link? Each link also decrease the potential by 1, so that you get this. And you see, things cancel really nicely. Link minus with link, cut minus with, cancel with cut. And you get 5. So the upshot is that, you see, amortized cost for insert is just 2. For delete min is log n. But for decrease key, it's also 5. This is an amortized cost, which means what? It means that when you bound like a AI, right? And if you want to sum up, yeah, it just means that if there are n insertions, n prime decrease delete min, and m decrease key, the total cost that you're going to pay is just going to be n times constant 2, n primes times log n, and m times 5. So that's what we get. That's what it means by amortized cost, actually. Question? Yeah. Yep.
How do you initially come up with the potential expression? Is that something that you just kind of think of on your own?
Yeah. There is no automatic way to come up with it. This is kind of art of designing algorithm now. Yeah. This is not even designing algorithm. It's designing analysis. Yeah. I don't know how, but you will see some of the exercise in the homework. Yeah. Okay. So now you see, once you have this, we can if we apply this to Fibonacci heap to Dijkstra algorithm, right? If you remember Dijkstra, you have insert, n delete min, and m decrease key. So the total time here for insert is just n times constant, n here times log n, and m here times constant. And this is why we get m plus n log n, as we promised from last week. And just to help you get the feeling of how to design potential function, I encourage you to try yourself. Try to see what if you change this constant to 1, to 3, or to 1.1. So this thing will be fine. But if you use it to be 1, things will go wrong. You should see yourself what goes wrong and why things break down. Also, I show how to use potential function to get amortized update time. You might try to use bank account method to show small amortized update time. The hint is that if you try to put $1 for each root of the trees and $2 for each marked node, that will work. Okay. One last thing about this is that, actually, one general thing I want to mention is that, okay, this week we talk about amortized analysis. Whenever you see any data structure with amortized guarantee, actually there is always the next question. That is, can we get the same time, but instead of amortized, we get worst case, right? Can we de-amortize this time bound? Yeah. And yeah, that's always a kind of the research question one can ask. And for Fibonacci heap, it turns out that it is the case. In, I think, stock 2012, people show how to get this time, which is constant, but it's worst case. So that's cool, but it's complicated, so I don't teach it. Okay. Good. Any question before I move on to the new thing? Okay, it's gonna be another cool data structure from the 80s. Like Fibonacci heap is from the 80s. It's by Bob Targent. He's like the big shot in data structure. He's the one who designed depth first search and a lot of basic stuff that you use in everyday algorithm. And this one, Splay tree, is one of the most magical data structure, I would say, that people still don't understand it fully up to now, but we will see what it is. It's called Splay tree, also called self-adjusting. It's one of something that is called self-adjusting binary search tree. So let me review a bit what is binary search tree, right? Everyone knows, but let me review it. So binary search tree is just a tree. It's binary tree such that each node have some value on it. And if you look at any node, then everything on the left subtree must be less than the key here, and everything on the right subtree must be more than the key of that node. Okay? And so it will always store some order set. Okay? And everything that is small is kind of on the left. Everything large is on the right. It can handle a bunch of operations like insert, delete, predecessor, successor, and everything. Today, we're just going to focus on one operation, the most basic one, which is lookup. Okay? You want to check if a node is in the set or not. And the time that you need to spend when you want to look up, let's say for 10, is just the depth of this. Right? You kind of keep going down the tree, so you pay like the length of the depth, the depth of this element. That's the cost. Okay. Another thing that I want to mention is how to view BST in a cleaner way. I'm not sure you have seen this. So I want to say that once you have specified the relative depth between any keys, by relative depth I mean that you say that which key should be deeper or higher than another key. Okay? Then actually, if you specify that, then the structure of BST is determined, is unique. What do I mean by that? Here, like this is just a number from 1 up to 23, and I said that, okay, I want this guy to be the highest. Then it means that this must be the root, right? Because it should be on the top. And now, among this interval, this guy should be the highest. Among this interval, this guy should be the highest. So, for example, if we know this, then you know that 14 must be the root, and the children of 14 must be just 6 and 22. You see? Can someone tell me what should be the children of 6?
1 and 10.
1 and 10. Yeah, because 1 should be higher than everyone here, and 10 should be higher than everyone here. So 1 and 10. How about children of 22? Anyone else? Yep.
16 and 23.
Yeah, exactly. Yep. Good, thanks. So yeah, you can go on like this and you keep going. So the point is, yeah, if you, like the key are sorted anyway, but once you kind of fix which one should be higher, then these edges are just determined. Okay? So this view can be a bit clearer because when you think of binary search tree, you can think of this relative depth and kind of forget about the edge, how things are connected. It's determined anyway. Okay. So now, so optimal binary search tree, right? So the runtime to look up any element, you can make sure that it's always at most log n, because you can make sure that the tree is balanced. You can use redback tree and AVL tree and so on. So the worst case time is log n. But you have seen before in this class that if you know the distribution of how you want to look up the trees, like this balanced tree may not be optimal. For example, if you want to access 1 half of the time, access 2 1/4 of the time, and so on, right? Then you can actually use dynamic programming to compute the base tree using this. And in this case, the base tree is like this. So the optimal tree can be very unbalanced. Okay, but it's solved, right? If you know the distribution, then you can come up with the best tree. But the question is, what if you don't even know the search distribution, the search probability? So you cannot just use dynamic programming to carefully construct the optimal tree. So what do you do, right? This is the ambitious goal that we want to achieve. I will show you one algorithm, which is called Splay tree, that kind of automatically learn this search distribution. And at the end, its cost, or actually its amortized cost, is still going to be as good as the optimal tree that you use dynamic programming to come up with, up to constant factor. Okay. So it's going to be, that's really impressive because it kind of automatically learn this thing. And you will see soon that it will actually learn other structure of the lookup sequence, even without any explicit information of the sequence. Okay, right now it's not super clear how it look like. Let's see now. My point is that it's super strong. Okay, let me describe this algorithm. Okay. So the first operation that you need to know is rotation. You have seen this, but I will tell you again. So suppose that I want to switch, I want to rotate x and y. X and y is an edge. Okay. You might have seen that, okay, how to rotate, you need to change the pointer here and there. But what is rotation? It's really just switching the depth of x and y. That's rotation. And once you switch the depth of x and y, then there is a unique way to reconnect. Right? That's why I said it's better you better think about how the relative depth and not the edge of the tree. Okay, so switch the depth. That's rotate. And now, whenever the algorithm, this Splay tree algorithm, whenever you want to look up for x, what I would do is to call something I call Splay x. That's the important operation in Splay tree. Okay. And what Splay x look like? It will, in high level, will keep rotating x to the root and do that 2 edge at a time. So there are a few cases to consider. So let me describe. So the first case is when the parent and the grandparent of x are on the same side, either less than x or both more than x. In this case, they are both more than x. Okay. So in this case, you see that the height, the height of p and g are more than the height of x. So what you make sure that will happen is that you make sure that the height of x is more than p and the height of p is more than g. That's what I will do. Okay. Look at 2 edges at a time, and if p and g are on the same side, then do this. And then once you do that, there is a unique way to connect them. Clear? Question?
So, like, if there was like more than one in between node, then it would just all those in between would be the same, right?
Yeah, everyone here. Ask again. Sorry.
If you have like more than one node between X and G.
X and P.
X and G.
G. No. Like G is literally like just the grandparent. So there is only one node between X and G. Like P is a parent of X, and G is a parent of P.
You're like just defining it to be like with 3 nodes, right?
Say it again.
Like you're defining the operation to like work specifically on like 3 nodes.
Yeah.
Okay.
Right. Yeah. So good. So this is called zigzag. They call it zigzag. I don't know. But another case is when the parent and grandparent of X are on the different side. Like this guy is less than X, this guy is more than X. Then what you do is just to make sure that the depth of X will be more than both of them. The height of X is higher than both G and P. So, and you get this guy. And then the last case is, so this is called zigzag. The last case is, okay, what if there is no grandparent? Then you would just make X higher than your parent, which is just to rotate basically. Okay. And then Splay operation basically keep doing this, like do it 2 at a time. If like you have X, if your grandparent and your parent are on the same side, do zigzag. X is moving up. Now look again. If the parent and grandparent are on the different side, do zigzag and move X up. Keep moving X up to the root in this way. Let's see example like this. In this case, you keep doing zigzag. Like do a zigzag, do it once, do it twice, do it again, and you see like that's when you're done. X is become the root now. If the tree is like this, then you keep doing zigzag. Do it like this. Do it again. And now there is no grandparent. So what you do? You just do one zig. Okay. Does the operation Splay make sense? Okay. So let's see some some demo. So yeah, so suppose that you start with like the worst possible tree, look like this, right? And what will happen if let's say I look up 32, then the tree will look like this. Maybe I look up again. So you see like the tree will become balanced pretty quickly. This is how it looks like. And can someone tell me what is the worst case lookup time for Splay? I keep playing until you answer.
Would it be 11?
Yeah. Why again?
Because like, I think if it's like the first scenario where it's like all in one line, it would be 11.
Yeah, exactly. And you actually can create this scenario just by like do sequential access like this, like keep doing, you know, like make the tree as fast as possible. And but okay, I do like it takes a lot of effort to make the tree bad. But if I go to this guy and click, then the tree become good pretty quickly again. So yeah, that's how it's like. Okay. Well, looks cool, but how do we even analyze it, right? So let's do that. And the main claim is this about Splay tree, which is this is a lemma which is super powerful. So let me state the lemma and you see if it makes sense. So the lemma says that if you just come up with any weight function at all, it's just some weight that map the key to some positive number, and then let W be the total weight. Okay. For any weight function you choose that, then the amortized time of Splay, amortized time to Splay x is at most log of W over W of x, log of total weight over weight of x. Okay. What does it mean? It means that the x is some potential function such that the amortized cost, which is the real cost, plus potential increase is just this much. That's what it means. Okay. Question about the statement? Okay. Before I prove this, let's see why this is so strong. The first implication is that the amortized lookup cost is just logged in for Splay, meaning that this algorithm is as good as like any balanced binary search tree. Why is that? Suppose I just set the weight of everyone to be 1. So total weight is n. Now, amortized cost of splaying any element is just log of W over W of x. So that's log n. So Splay is as good as balanced binary search tree in the amortized sense. Okay, good. And now I want to say that it's not just as good as a balanced tree, it's as good as any tree. It's a static optimal. So just look at the setting where you do dynamic programming to solve binary search tree, right? To get optimal binary search tree. Let's say that the key xi is searched with probability pi. You can then use dynamic programming to come up with the best BST. But actually, it's known that I don't prove this, but it's known, okay, that even the optimal binary search tree will have expected cost to look something like this. The expected cost looks like this. This is also called entropy. It is something that range from, it can be constant. Actually, it can be like a 0 up to log n. So maybe you think of it as constant, yeah. Constant up to log n. So like basically the intuition is if your distribution is very skewed, like you access like a 1 most of the time, let's say, then the entropy will be constant. But if the distribution is like a kind of uniform, the entropy will be like log n. Okay. That's the cost of optimal binary search tree up to constant. And now, okay, this is the best. Like given any search sequence, you can compute the frequency of the search sequence, and then you know exactly what is the best possible tree, which cost is like that. Now I want to say that Splay is as good as this tree. How to do that? Just try to set the weight function of xi to be pi. So the total weight is now 1. Now excess lemma says that amortized cost of Splay to Splay xi is this thing, which is log of 1 over pi, which means that the expected amortized cost in expectation, this thing is just going to be the sum over like this thing, right? Pi times this. But that's just the same as the optimal binary search tree up to constant. So you see, like, the proof is so simple, but immediately you get, boom, it's optimal. Okay, so yeah, I just repeat again. For any search sequence, the cost of Splay is just constant times the cost of optimal static binary search tree. And you see, this algorithm is just oblivious from the sequence. It doesn't even know the sequence ahead of time. It's just, and yet it kind of adapts to it. Okay. Super cool. There are many more stronger implications. I will let you try to look up and see it yourself. But intuitively, if you access x more, if you access any element more often, then x is going to be cheaper, and some more strong properties. Anyway, let's try to prove this excess lemma, this thing. Okay. So we want to say that the x is a potential function such that this is true. And the magical potential function look like this. Not clear how to come up with it at all, but the goal is that you should see that it at least makes sense. The potential look like this. First we define the rank of, this is just some definition, okay? The rank of any node is log of the total weight of element in the subtree rooted at x. Okay. Just to make sure you understand, if this is 3, if this is x, call this thing tx, is the total subtree rooted at x, then this thing is a log of sum of the weight y when y is in tx. That's the rank. And our potential is the sum of the rank. So, okay. I don't even know how they come up with this, but you will see that it works. Okay. So what I'm gonna show is that let's try to analyze it a bit. Okay. The first thing that I want to show is that the potential, like when I do zig-zag, what I want to do is to analyze how the potential change. And at the end, I want to show that the potential change in this way. It increased by at most 3 times the rank of x after I do zig-zag minus the rank of x before I do the operation. So I call this rank prime. It's just the rank of x after zig-zag operation, and rank is just rank before. And also I have -1. So let's do that. Let's do this. Okay. So why it look like this? So first of all, the first observation is that there can be like even some node above G, right? and so on. And there are nodes here. Like there are some tree above. But the first thing to note is the rank of every node stay the same, except the rank of X, P, and G. Right? The total weight of the subtree, like for any node, the total weight of the subtree doesn't change. If it's here, the total weight doesn't change. Any node here, it doesn't even change. It doesn't even see any, like anything below it doesn't change. And if it's even above G, you just rearrange something below you. Not the total weight doesn't change. The rank, the guy that have its rank change is just X, P, and G, which means that how much the potential change is just rank after of G minus rank before. And the same for P and the same for X. Make sense? Then you can see that rank prime of X, which is here, is just the same as rank of G before. So you do some cancellation. Rank prime of X cancel with rank of G. Get that. And you calculate a bit more. Because like rank of X is less than rank of P, you get this thing. Rank prime of P is less than the rank prime of X because P is below X. So you get a bunch of you do some calculation, and then this is the important point. You have this. So how to get this? It involves some calculation, which I will show you. But the important point about all this is that you will see soon that this -1 term here is very important, and we need it. So let me try to calculate for you how to get this. So the calculation is like, the first thing is to note that this thing square is at least, right? Because this is true just because like for any number a and b, a minus b squared is at least 0. So when I rearrange a bit, I get this. Which means that when I take log of AB is at least log of A plus log of B plus 2. Okay. And now let's see that the rank of x prime. Okay. So let me call like rank of x prime kind of sum this thing up, right? Okay. So let me say that maybe let me first define rank of G, rank prime of G. Rank prime of G is like this subtree. I call this thing B. This is kind of just log of B. Okay. And then rank of X. Rank of X is something like here. I call it A. The total weight of this subtree, I call it A. So the rank of X is just log of A. And you see that rank prime of X, which is everything here, this is at least what? Log of A plus B. Make sense so far? B is just the total weight here. A is the total weight here. and the rank is just a log of the weight, the total weight. But the rank prime of x is the log, like it combines both of them. But now, using this thing, it means what? Means that rank like 2 times rank prime of x at least rank g plus rank x plus 2. Okay. Now you use this inequality and just kind of combine it with this guy. Okay. Like basically just write it in such a way that this whole thing minus this thing is at least 0. So like this thing minus this whole thing is at least 0. Add it into this, like rank prime of g and rank prime of g will cancel, and you get this thing. I think you even get minus 2 here. So point is that you do some calculation and you get this. But the super clever thing about this potential function is that they do it in such a way that the potential change after doing sig gives you this minus 1. Intuitively, when you have potential decrease, it means that you get money for you, right? Like this decrease in potential will pay for your real cost. This is the minus 1 here is important. Yeah.
How do you get rank prime x greater than or equal log a plus b again?
So what's the total weight of x after you like the total weight of x in this subtree, right? You have like this is basically a, and this is b.
Okay, so it's just a plus b plus weight of p.
Yeah.
Okay, sorry.
Okay. Okay. So it doesn't matter too much. It's just some calculation, but I just want to do it for you once to see how things work. And just note this down. You get this change in potential. If you do it for zigzag, do some calculation, simplify like similar to before, you get the same thing. Okay. You have minus 1 here. How about zig? You get similar thing, like this thing, but without minus 1. Why do we do this at all? Let's see. Suppose now I want to analyze the potential change when I splay x up to the root. Okay. So let's see how the potential change. First of all, when I splay, like when I splay, I do a bunch of zigzag and zigzag. Potential change will be like this. When I do zigzag, potential change, you get this increase and this decrease. I do it again, I get this increase and this decrease. This thing cancel. Do it again and again, you get like this thing will be cancelled, and you get the next thing, rank triple prime and so on. Right? So you basically get this cancellation. You get a telescoping sum, and at the end you get that the change in potential is this guy minus this guy, because everything in between like get cancelled. But actually what you get also is what? You get this thing, right? But also minus, this is important, minus the number of zigzag and zigzag. Because every time you do zigzag and zigzag, you also decrease your potential by 1. Okay. And basically you will use this thing, the decrease in potential here, to pay for your real cost. Right? You think like this extra -1 in potential change will be offset to like the real cost of +1 here. Because when you do sig once, that's just constant time, right? It's just constant time in the real cost, but you just use this potential to cancel because potential decrease. Okay, so that's what you get. So it means that the amortized time, which is the real cost, which is just the number of zigzag and zigzag, right? Plus the change in potential. It's just something like 3 times this thing, plus just constant. Why? Because the change in potential here, you have this term and minus this thing. And you get another constant because you might do sig only once. That's why you get constant here. But even though you do sig and zigzag many times, this thing cancel. Make sense? You have question?
Wait, sorry, what happened to the 3 factor?
Yeah, I forget to write 3, yeah. Yeah, it's just some add 3 to everything here. So you need to understand up to here. Okay. So now the rank of the root is just log of W. The rank of X is just log of the total weight below X. But total weight below X is more than the weight of X itself. So you get that you get this thing, which is just O of W, log of W over W of X. Okay. So that's why we are done. We get the excess lemma. But you see, like, the most important thing in this analysis is that although you would do zigzag and zigzag many times, the potential will decrease proportion to that number of zigzag and zigzag. So that cost just cancel, and the amortized cost is then small. Okay. So now there are like some very important open problem called dynamic optimality that I want to mention to you very quickly. So for like, you see that Splay is as good as any optimal static BST. Then the conjecture is Splay is also as good as any optimal dynamic BST. What do you mean by that? It's just the tree that you allow rotation as well. Because Splay kind of rotate, right? But you kind of compare yourself, Splay, with static tree. We want to compare it to dynamic tree as well. This is a conjecture that no one can prove up to now. And if you can, I will give you a PhD. It's really, you can prove it. Let me tell you a bit why it's nice, like why power, like dynamic BST is powerful. Just consider simple example, like when you want to access 1, 2, 3, 4, 5 up to n. Just access sequentially, right? This simple sequence will cause any static BST at least n log n, because like most of the nodes will have depth at least log n. So you pay n log n. But if you allow rotations, you can pay n. And why is that? Just do something like this. You start your tree with something like this. Axis 1, rotate once. Axis 2, rotate once, and so on. So the cost is just constant per time. And there are many other cases when dynamic BST is stronger. Like you get much better bound than n log n. Now dynamic optimality conjecture says that, okay, forget all this dynamic BST, just use Splay tree. It's just as good as any algorithm. It's like the algorithm, BST algorithm that rules them all. So we don't know yet how to do that, how to prove this, but yeah, that's the very nice open problem. And you see, this is a cool data structure with really crazy analysis that potential function just kind of come out and you don't know how to come up with it, but you can analyze it and verify that. But at least from this class, you should try to get intuition that this thing makes sense. Because once you do that, it gives you some hope that you can solve, like you can come up with some potential function on your own. Okay. And with this, let me move on to the last thing. So last thing is about dynamic graph algorithm again, because I like it. So the problem that we're going to look at is edge orientation problem. In this problem, you have undirected graph, n vertices and n edges, and it's undirected, but the orientation g arrow of g is just the same graph, but you assign direction to each edge. And our goal is to find orientation such that the maximum out degree is small. And I say that delta orientation is just orientation with maximum out degree at most delta. That's just the definition. Now can someone tell me why any tree has a one orientation? If the graph is a tree, there is a one orientation. How to do that? Yep.
Well, there has to exist like a root, right? So you can wait. I was saying that you just like put everything inwards towards the root, and then like take anything at like that's a leaf, and then point it outwards.
Yeah, good. So let me repeat that. So if you have a tree, first of all, you can just root it at any node and write down the tree. Write the tree like this. And then, what if I just point everyone to its parent? Then the out degree of everyone now is just 1, except the root, which out degree is 0. Okay. So that's very simple orientation. And actually, any planar graph will have small orientation as well, but I will not show you. Okay. Now, why is it nice to have like a small orientation? So consider this very simple problem when you have a graph and you want to check if U and V are adjacent or not, right? If you use adjacency matrix, you can check this in O1 time, but the space is n squared. which can be much more than the size of your graph when the graph is sparse. And if you use adjacency list, even sorted one, okay, the space is linear in the number of edges, which is nice. But to check this, you might still take log n time to do some binary search. Can you do like a best of both worlds? Constant time and linear space? And yes, you can if you have O1 orientation. How to do that? Can someone tell me?
If you're given an O1 orientation, that means for every vertex has a constant number of neighbors. So just store them.
Yeah. So like you might have a bunch of in degree. Like it can be n, but the out degree is small. And now, okay, out degree of this guy is so small, although there's a lot of in degree. Now you know that this edge between u and v must point out to some from u or from v. So all you need to check is just look at all the out neighbor of u and all the out neighbor of v, and check if like they are adjacent or not. Each of them take constant time. Okay, so just scan the out neighbor of both u and v, and you're done. In general, this thing is like useful, but now the problem we're going to look at today is that suppose you have a graph, directed graph, and this graph is dynamic. You might delete or insert edges at a time. And suppose I promise you that this graph have very good orientation. Let's say C. Think of C as some constant. C orientation. What we want to do is at any time, we want to maintain 5C orientation of this graph. That's the goal. So before I tell you the algorithm, let me give you some observation. The first thing is that if you have a graph and if it has C orientation, then first of all, there can be at most, the number of edges is at most NC. And the reason is simple, because you know that the X is a way such that each node point, like each node have at most C out degree. So each edge, like it's like every edge will be like a out edge of some node, but each node can have at most C out neighbor. So the number of edges in total must be Cn at most. Make sense? But it's more than that actually, because I claim that for any set, actually, for any set in this graph, S, the number of edges in this induced subgraph, the number of edges such that edges are both inside S. Okay. The number of edges inside this induced subgraph G induced by S is going to be at most C times S. By the same reasoning, like every edge inside S will be responsible by some node in S. Each node in S have only C out edges. So that's the number of edges inside any induced subgraph. Okay. So now comes the important lemma. Okay, suppose that G have C orientation, but let G arrow here be some orientation, might be bad orientation. Like, might not be C orientation. In particular, suppose that there is some node in this orientation, okay, without such that out degree is more than 2C, much more than C. Now I claim that there will be another node x whose outer degree is at most 2c. And you can find a directed path from u to x, and the length is just log n. So it's like kind of short. You have u. This guy have large outer degree 2c. This is x here. Outer degree is strictly less than 2c. And there is like a directed path here. That is short from u to x. This is like a at most log n. That's the claim. So why this is the case? The way to go is just let me define vi to contain every node such that the distance from u to v is at most I. So it's like a ball around u of radius I. But this is a ball in G arrow. Right? It's like directed ball. So suppose that this is not true. Suppose that the lemma is not true. It means that even if you grow the ball by this radius, every node in this ball have outer degree more than 2c. Now, I want to say that something must give you contradiction. So, if that is the case, I will claim that the ball, like the ball of radius I plus 1, will double the size compared to the ball of radius I. And if that is the case, you cannot double too many times, not more than log n times, because otherwise there are just n nodes in the graph, right? You cannot double too many times. So why this is true? The reason is that if you look at vi here, and let's consider all edges that going out from vi to any node. So the edges that might go out of vi, some edge is in vi. Just collect all these edges. Okay. So this is my set G, EG of vi going out from vi to any node. Okay. My claim is that if you look just at this set, which is in the graph induced by vi plus 1, all red edges here will be inside the orange circle. Why is that? Because if this is u, right, everyone in vi have the path of length I from u. And if you might just go out of this set, but it's just now the path of length I plus 1. So the guy here is in vi plus 1. And now, if I just look at the graph induced by vi plus 1, all the red edges here is just inside this graph. Make sense? I claim this thing. Question about this? It's good or not clear?
Sorry, could you please repeat?
Yeah. I mean, does the notation make sense at least? Okay. Well, now, so I claim that every red edge here, the red edge, which is just all edges incident to vi, like going out of vi, must be inside the graph induced by vi plus 1. And the reason is that every node in vi, right, can be reached from you using I step. It's just the definition of VI. And now, what about this edge? This node here must be in VI plus 1. Just because this is a part of length at most I plus 1. Which means that this edge in particular is in this graph. The graph induced by VI plus 1 is inside, both endpoints are inside VI plus 1. The edge that are, yeah, so that's it. Yeah. Okay. And once you have that the number of edges here is at most the number of edges in this graph. But what's the size of this graph? It's at most C times VI plus 1. What's the number of edges here? At least VI times 2C, because every guy have outer degree at least 2C. We assume this. Combining this together, you get this. VI plus 1, cancel C, you get that VI is at least 2 times. VI plus 1 is at least 2 VI. Okay. Now means that the size of this is at least this thing, double at each time times V0. V0 is at least 1. That's more than n. That's impossible. So that's why this lemma must be true. That is, given any node U, you must be able to find some guy close to you, such that the outer degree is small. Okay. So now, let me tell you some slow algorithm. So this is now dynamic algorithm, right? Well, if you have to delete any edge, just delete it, nothing. But if I insert any edge, let's say that I just assign the direction from U to V. This is arbitrary. But if I do that, our degree of U might increase more than 2C. Like I want to claim that this algorithm maintains 2C orientation. As long as everything have our degree less than 2C, that's good. But now if I insert a new edge and I direct from U to V, our degree of U might be more than 2C because it's a new edge. But if that happens, what I will do? We know that there exists X whose degree is less than 2C. Okay. So actually, if our degree here is 2C plus 1, it's strictly more than 2C by 1. You know that there is X whose outer degree is less than 2C. And there is a short path from it. So what I can do is just take U, look at X, look at this path, directed path. And then I flip edges along this path. So what happened to U? Now the degree of U, our degree of U now become 2C. Our degree of X will increase, but still at most 2C. Because it used to have less than 2C. How about our degree of everyone else on the path? What happened to them?
Stay the same.
Stay the same.
Change the direction.
Yeah, just change the direction. So you really just change the outer degree of X and U, and that fixes the problem. So you see, like you get this algorithm that maintains 2C orientation, and the number of flip is just 0 per deletion. You do nothing, and at most log n plus 1 per insertion. So that's cool, except that it's bad because not clear how to get this node X. Right? You just know that it exists. If you grow the ball, you might need linear time to grow the ball and find this node X. We don't want to pay linear time. Okay. So that's slow, but at least it has like a good good number of flip, but it's slow. So that's the problem. Now we will actually exploit this slow algorithm somehow. But now let me tell you a totally different algorithm that I claim will maintain 5C orientation. Algorithm is this. When you delete, do nothing, just delete it. And when you insert, just say like you just assign direction from U to V again. But now I do something very stupid. You just say that as long as there exists a node W that have outer degree more than 5C, I reset. And by reset, I mean just make the outer degree of this guy to become 0. Okay. That's the algorithm. Keep doing this until no one have outer degree more than 5C. And now the trivial, like the correctness is trivial, because you just make sure that no one have outer degree more than 5C. But why this algorithm is fast? Like this looks like some propagation can happen, right? You reset this node, it might now increase the outer degree of some other node, and so on. You might like keep resetting a lot of time. So my claim is this. Claim is that the number of reset must be small, actually. So if I say that let Ni and Di be the total number of edge insertion and deletion, I claim that number of reset is something like Ni times log n over C. Claim that the total number of reset is not too big. You will see this claim soon, but if this is the case, why this is good? Because the total update time throughout the whole sequence of operation, first of all, each deletion you spend constant time, that's good. And each insertion you would spend constant time, except that if you reset, you would spend something like 5C time to flip all the outer degree that is more like around 5C edges. For each reset, you will spend this time. Right? But the number of reset here is small. We will prove this soon, but the number of reset, if this is true, this is something like Ni log n over C. So you sum up and you get this total time. Which means that the amortized deletion time is O1, amortized insertion time is just log n. Okay, so now let me prove this claim. That's the only thing we need to do. Okay. So what I will do is that I will define edge to be bad if slow and fast algorithm assign different direction to an edge. So this is important. Like you run fast algorithm, you just imagine that you run slow algorithm. Slow algorithm is just for your analysis now. Okay. Imagine that you have the slow algorithm that run for you, and now an edge is bad if slow and fast algorithm disagree. Otherwise, I call it good. But good and bad here is just for analysis. You don't even run the slow algorithm, right? Okay. And the potential function is the number of bad edges. So now, my claim is that we need to analyze this potential function. So let me take like 3 more minutes. I'm going to be done. I need to, sorry. So the total increase in potential, I claim that it's going to be at most this. Okay? If you count like only how much it increased, it might decrease sometime, but if you count whenever it increased, how much is that increase in total? It's at most this thing. Why is that? first of all, each deletion cannot increase the potential. When you delete, there is no new edge. There is no new bad edge. That's good. When you insert, okay, I can increase the number of bad edges by this much. Why? 1 from the new edge that I insert. But once I insert, the slow algorithm that you run in your imagination might flip edges, but that's just log n edges. That flip might introduce new bad edges, but that's just log n. So this is how much the increase in potential might happen for each insertion. Just something like log n. But now I claim that for each reset, you will decrease potential by C. And the reason is this. When you reset, right, you have a node U. Its out degree is like 5C. Now, how many guys here are good? At most 2C. Because if you look at the slow algorithm, it maintains 2C orientation. So the out degree of the slow guy is at most 2C. So at most 2C here can be out. So this can be, only this 2C guy is good at most. Everything else here in the slow guy, it must be in, although this is out in the fast guy. So all of this is bad. At least 3C bad guy. And what you do is that you're gonna flip all the blue edges, right? It means that the good guy become bad, but there are good edges that become bad, but that's at most 2C edges. So that increase your potential by at most 2C. The bad guy will become good, but that's a lot. That's at least 3C. So now it means that you decrease by at least 3C, you increase by at most 2C. So the total decrease is at least C. That's why this is the total increase, but each reset will decrease it by C. So the number of reset is at most this over C. So that's complete the claim. Yeah. So the exercise for you is you can try to improve this constant 5 to something else. I believe you can do something like 3 or 2. I'm not sure, but yeah, that's possible. Just to make sure you understand this whole thing. Okay, so next time is going to be next thing, randomization. Yeah, thanks a lot.